All right, so how about this calcium regulation? This is an older experiment done prior to many of these experiments where we can watch individual vesicles release. So it's done in isolated synaptosomes. And so the synaptosomes are prepared as a gamish and centrifuged at differential centrifugation at high speed to pull the synaptosomes out from other particles, other subcellular particles. And 2 assays are done in this experiment by Cousins and Robinson. And one is to take the synaptosomes and measure glutamate release from them upon stimulating them or depolarizing them with potassium chloride. Now, different concentrations of potassium chloride cause greater amounts of exocytosis, as one would imagine from greater depolarization. Similarly, they use 4-aminopyridine or ionomycin, which is a calcium ionophore, to stimulate release. And you can see glutamate release under all of those conditions. In order to look at endocytosis, they load the vesicles with one of these FM dyes, and they look to see how much loading they got under these different conditions of potassium or ionomycin or 4-AP. So they load the synaptosomes under conditions of 5, 10, or 30 millimolar potassium chloride with the dye, and then they use a fixed amount of potassium chloride in a second stimulus to unload the dye. And under these conditions, they take the initial intensity as a 0, and they look to see how much intensity is lost as the dye leaves the vesicles which have been exocytosed. And they find that they take then the ratio of the amount of dye that's released to the amount of glutamate that's released, and they can plot that. So they're looking at the amount of dye that was taken up, that one can see now being released to the second stimulus, as a measure of how much endocytosis there was. And this ratio of the amount of endocytosis to the amount of exocytosis is what is plotted in these bar graphs. And surprisingly, that ratio is higher for the lower concentrations, or the less depolarization, and it's least for the most depolarization, or the conditions in which there's most endocytosis, which tells us that there is less exocytosis relative to the endocytosis, and that these conditions, especially the ionomycin one, gives us a calcium dependence. We would think about calcium dependence in the potassium as well, because the more depolarized the synaptic terminals are, the more calcium is going to come in. So all of these show in conditions which would have a greater intracellular calcium, there is actually less endocytosis, leading to the idea that high concentrations of calcium inhibit endocytosis. Cousins and Robinson's diagram this to help you conceive of it as also a spatial problem, that at the active zone, where calcium we know is quite high, and the process of vesicle fusion is going on, we want, or biology wants, an efficient release process, and may not want to crowd that active zone with actively endocytosing vesicles. So a high calcium inhibiting endocytosis would favor the movement of those vesicles laterally and fusion with the plasma membrane, so that endocytosis, as perhaps a clathrin-mediated event, or possibly still even a kiss and run type event, might happen in a non-active zone lateral to the central part of the active zone, and that the calcium sensitivity would be such that the high calcium prevents endocytosis in one place, but laterally, where we know the calcium concentration goes down, endocytosis would be favored. And indeed, more recent measurements of following individual vesicles shows that there is much less endocytosis at the center of the active zone than lateral to it. In other experiments, Cousins and Robinson go on to look at influences of other calcium-mediated calcium regulators, cytosolic, calmodulin, calcineurin, etc., as well as influence of various proteins necessary for clathrin-coated vesicular endocytosis. And they suggest that there is not only the calcium dependence of release, but the calcium dependence of inhibiting vesicular endocytosis in that active zone. And that there may be some kind of a maintenance phase which would keep the vesicle membrane somewhat intact if kiss and run were to occur laterally. So besides the frequency-dependent, calcium-dependent, and possibly phosphorylation-dependent regulation of the balance between kiss and run and full collapse infusion, there may be physical controls on the synaptic vesicle that limits the mode of vesicular release. And here we consider the connections between individual synaptic vesicles, which are tethers that are due to the protein synapsin 1, and there's numerous isoforms of synapsin 1, and previously the idea was that synapsin 1 tied synaptic vesicles to an actin cytoskeleton, which indeed it does as a storage pool. But more recent studies show that vesicles are tethered to each other even very close to the active zone, so that this tethering may induce some kind of force on the synaptic vesicle closest to the presynaptic membrane and prevent its full collapse and fusion. In other words, this cytoskeletal tether may actually favor the kiss and run type of behavior. And the other point that this figure makes is that after a kiss and run event has occurred, the snare proteins don't necessarily continue to reside in the synaptic vesicle, that many of them may be lost to the plasma membrane and contribute to a very slow depletion of vesicular components for synaptic vesicle fusion. So one can think about, it's a different way to think about where the molecules end up after the fusion event. But this also gives us a way to begin to think about kiss and run as an intermediate state between the docked and primed vesicle and a vesicle that is beginning to undergo full collapse and fusion irreversibly. If one thinks about kiss and run as a reversible state, then after the synaptic vesicle reaches the plasma membrane, is resident there for a while, has at least one set of snare proteins to tether it to the membrane, and so it could be considered to be primed and docked. The complexin zippers up, and we might get, in a calcium-dependent manner, a kiss and run type of opening. However, only one snare complex would be needed for this kind of release, and therefore it would not necessarily be complete and would be reversible. However, a different set of calcium-sensitive events might, or additional zippering of additional snare complexes, at least 3 are needed, if not more, would be, if that occurred, then the vesicle would proceed from this intermediate state to the full collapse and fusion. And this indeed might be the case because we see more kiss and run, and certainly flickering, that happens before the full collapse and fusion event. So one doesn't necessarily need to think of this as an either-or kind of mechanism, but one that is sequential in one way or another and governed by the same physical-chemical laws that govern all of the biological phenomena that we've been considering.